Here's our feedstock for our penny laps. So I went and separated all my pocket change, and you need pennies that, or US pennies I should say, that are older than 1982, okay? And so here's the difference. Here's what they look like when you scuff the back of them. This is just to get the glue to adhere better. But you can see there's a colored, actually maybe this is not a good, here's one that has maybe a better, yeah, there we go, those are better. You can see here, these are pennies that are, I think these are 82s, yeah, 82s, and they have zinc in them, and we really don't want that. We want as much copper as possible, so these are older than 82, so 81 and older, so what's that one? 70, 75, yeah. Anyway, I'm scuffing the backs and then we're going to glue them down. So no zinc. Those are go away. All right, so we're prepping these pennies to glue them down to these platens here. Now I want to do 2 penny laps and then 1 with the copper washers. It's more of an experiment on my part. The copper washers are actually kind of nice. They're really uniform and they have a hole in them, which is kind of cool. This gives us a little more surface area when they're machined off, but anyway, I'm just trying this. This is kind of a side experiment. So I've sanded the backs and kind of roughed them up in preparation to glue them. But what I want to do now is take off some of this tarnish, you know, this the patina that's on these pennies. And what I'm going to use here is I got some copper cleaner here, and what this is white vinegar and salt. So there's a couple of 3 tablespoons of salt and then some white vinegar. And what we're going to do is we'll just drop these in my little cup here. Now you can see the tarnish on them now. Okay, it's kind of cool. This actually works really good. Let's get that out of the way. One more there? No. And then we'll just put some of this in there. Just enough to kind of cover them up. And you can already see, I'll bring you in closer. You can already see the effect. It's pretty immediate. Alright, so. You can see they're already brightening up. So all that Vergis is kind of coming off. Anyway, that's a nice trick, the white vinegar and salt. If you have to clean copper in the home shop, it works really good. Now, it doesn't give it a bright finish like Bright Dip, which is a commercial process that uses a, oh, you know what? I don't know what they use actually. Some kind of chromate something or other. Anyway, this works pretty good. So we're going to rinse these off and then dry them off, and then we'll glue them on. Just going to clean the lap prior to bonding these down. And then I'm going to put this is just basically a fence to keep me honest around the edge, at least for most of it, as I'm gluing these down. You know, I was trying to use tweezers on on this one here, and the fingers are the best. This is a Loctite 380, and it cleans up with acetone, so it's not too bad to get it off. So I don't know, it's pretty straightforward. This particular industrial size here has a pretty good dispenser tip. You know, have to screw around too much. So you want to give it a little swirl. I get a big blob of it there, so I better put another one right there, right? And so it goes. You can glue your fingers together too. There's no, trying to be super neat with this is probably a exercise in futility here, so just make sure you get the prepped side down. The last couple are they're gonna hang over, so but we're not gonna stress out about it because we'll just trim those off. I suppose you could try to get it perfect, but I don't think there's any particular advantage to that. All right, that's probably good. So we'll just clip those off. All right, so let's let that sit, and we'll do the other one. See you later, Abe. Abe's got to go. Looks like we got a nice full cleanup there. And they're all copper. those zinc ringers in there. All right, put a little chamfer on that and I'll do the other one. All right, so we got them all faced. The pennies faced actually really easily. And as you guys noticed that I ended up, a couple of these fell off. And I think the washers are smoother, and they probably needed a little more prep than what I gave them. Ultimately, I got it faced off, but this was a no-brainer. They just went really easily, and I was able to chamfer them. So the shape on the back may contributed to it, or I don't know what, but they also have a little more surface area than these do too. But a couple of these popped off and I had to put them back on and then go back and redo it. So it was a little bit of a nuisance. But I kind of blame myself a little bit because I could have prepped the aluminum a little bit better than I did. It was just a smooth turn finish, and I didn't scuff it up with any paper. So these are actually ready to start lapping together. I'm going to label them and mark them with some increments, 8 increments on them, and then we'll start lapping these with the time saver, but the yellow time saver for brasses and coppers and bronzes and things like that. So off we go. Okay, so there were actually some really good questions that came through on Lapping Plates 3 video, and I thought I'd just address some of those now. Let's go ahead and do it. So it's a little bit of talking, so if you don't want to listen to talking, you can fast forward from here. So the first one was, about the wavelength of this particular light, this weird light here. So this is what we call a monochromatic light source. So it's light of a particular wavelength. And in this case here, it's helium light, which has a wavelength. And if you guys remember from your physics class, you know, a wavelength is basically that, right? Okay, so from there to there is a wavelength. Well, light, that's actually a measurement. That's a distance from there to there, okay? And we can measure things with light, which is really cool, right? And in this particular light, on this this light here is, let me turn it here. This is 587.6 nanometers, okay? That's the wavelength of this particular light, okay? By the way, that's pretty small. Nanometers are dinky, okay? So that's about 22 millionths of an inch. 587 nanometers is about 22 millionths of an inch, okay? So without getting into, you know, heavy-duty nerdville there, okay? What we're trying to do with these lapping plates is we want to get them to some fraction, flat within some fraction of this particular wavelength, okay? You know, and personally, my target has been a quarter wave of this particular light, okay? And what that translates into is, that's, that is let's see, I wrote it down over here because I couldn't remember, 0.15 microns, okay? So about 3 millionths of an inch, all right, and 0.15 micrometers, okay? And that's pretty small. Now, it's totally achievable, and with our optical flats, we can actually inspect and evaluate that surface, okay, for how flat it is compared to, and using this as a reference, okay? So this is our reference standard here. It's a known wavelength, so it doesn't need to be calibrated. It's kind of a, it's part of the electromagnetic spectrum, right? So it's our standard in this case, or length standard, I should say. Now, you know, as we flatten these and we get them flatter and flatter and flatter, right? Somebody brought up, you know, why is that one particular plate, not these guys here, the cast iron ones, why does it have that hollow in the middle? Well, that's just a natural process of the lapping. They're actually, they're alternating, and hopefully you can see this ruler here. They're alternating between concave and convex, right? Okay, now this is a great exaggeration, right? So the flatter you get, a little bit of lapping and it takes it concave, a little bit, and if you flip it on top and you lap it a little bit more, it goes the other way and it goes convex, right? So optical flats are actually marked whether they're concave or convex, okay? And which is pretty cool, right? Now here's the really neat part. This is the part I thought's really neat, right? So if you think about that, you know, you can never have something that's just absolutely pure, dead flat. Now you can have things that are dang flat, but not absolutely in the theoretical sense flat, right? So they're always going to be a little bit concave, or they're going to be a little bit convex, okay? Now we could be talking very, very tiny amounts, but they'll always be that way. So if we actually achieve this quarter wave that I'm looking for on these plates, just, you know, that's just a personal goal, okay? And it should be totally achievable with these techniques, okay? What that means is that radius that we're talking about, and this is really cool, right? That radius that we're talking about is something like almost 24 miles. The radius is 24 miles. Or 38 kilometers for our metric friends, right? So if you took that curve and you went and you walked to where the center of that curve was, it'd be 38 kilometers away. So now the optical metrology guys where I work, they talk in 100-kilometer radiuses. So these are incredibly flat things that they're fiddling around with there at work. So anyway, I just thought you guys would like that, and a little bit of background. We're gonna dig in deep to this because this is really interesting stuff, and for all us the fellow nerds out there, we'll dig into this and the optical flats a little bit better. And but I want to do the lapping plates and kind of focus on those. And then here's a blade that I got, just kind of, you know, I struggled with that carbide tip blade for cutting grooves, right? Well, this one's got a diamond edge on it, and this would probably work really well. I haven't tried it yet, but I was at Lowe's, and they had these, and it was, I don't know, it was 15 bucks or something like that, so I figured I'd get one and give it a try for cutting cast iron, okay? Okay, so we're looking at the cast iron plates now, and I've done a little bit more lapping on these to try to get rid of that little pesky ring that I was annoyed by. And there's still a halo of it, so I got a little bit more to do. So I put another hour into it or something. So I'm going to continue on, and then we'll repolish the plates, and then we'll check them with the light and the optical flat. Okay. Now, a couple people, I guess they didn't hear me in the first video. You know, hey, what's that material, right? Well, these are discs that came from McMaster Car, and I put the part number in the description, so you can look them up and buy them. They have them in different sizes. You know, I think you can get them up to 12-inch or something like that, and they're not particularly expensive. So if you want to try making a set of 3 lapping plates, you know, you can buy the material fairly cheap. Now, don't skimp on the thickness, because this thickness, it translates into stiffness, okay? So what you don't want is you don't want something that, you know, as you're putting a little bit of load on it or whatever, it's deflecting and changing too much, okay? So these are fairly rigid in the, you know, over this diameter and thickness here, okay? So, and another person said, well, gee, why didn't you surface grind those first? Well, yeah, you could do that. But my surface grinder only has 5 inches of transverse travel, right? So I would have had to turn the plate around and putz around with that, right? And as you guys saw, you know, from a lathe turn finish, I put 3 hours into it to get them, you know, down to, I don't know, it was about 1 band or something like that, or 1.5 bands, right? Which is pretty damn flat, right, in the scheme of things, right? So yeah, surface grinding, it might have sped it up a little bit, okay, but you know, I would have spent an hour or two, you know, grinding these all flat, right? So, you know, you're doing 2 at once when you're lapping. Yeah, okay. If you got a grinder, fine, grind them. You'll save some time probably. All right, but that's the reason I didn't do that, because I really wanted to do this with no tools, or no particular fancy tools, right? So guys that maybe just have a lathe, or maybe you don't have a lathe, right? I mean, frankly, you could start with these plates looking like this and start rubbing them together, and it would take you longer, but you would end up with flat planes, okay? So with basically, you know, if you're building a pyramid and you had rocks, right, you could rub these rocks together and end up with a bunch of surface plates, okay? So, and no measuring tools, right? So that, to me, that was kind of the attraction of doing this the hard way, so to speak, all right? And then, you know, everybody's a smart guy out there, or a smart person, all right? And they said, well, gee, you're using that time saver, right? You know, you could go really fast if you just switch to diamond. Well, you know, sometimes it's not about fast, it's about the journey, right? This stuff's cheap, and what I really wanted was I wanted something that wasn't embedding, right? So diamond tends to charge into the softer surface because it's so damn hard, right? And we're gonna show that with those copper laps, but I wanted something that didn't embed abrasive into the surface. So that's kind of why I chose this. And yeah, diamond's faster, hands down, right? You know, you want to go fast, use diamond, okay? But remember that whatever grit diamond that you are using, you know, some of that's going to be stuck in this plate, and it may come out, or it may cause you problems when you least want it to cause you a problem, okay? When you have a 30 micron scratch in a 1 micron surface finish, okay? That's when it really annoys you when something like that happens. So, so we're trying to keep these pure, you know, as far as we can take them before we get crazy with diamond on them. Ultimately, there will be diamond on these, but one will be, you know, maybe 9 micron, 6, 3, or, you know, I don't know, 6, 3, 1, something like that. I don't know. That's probably how they'll end up. And you can recondition them and get rid of the diamond, okay? So don't worry about that. But I just wanted to do it without diamond initially, okay? Okay, so then the last thing I wanted to address, you know, with the lapping procedure here is I got a foam pad underneath this, okay? So this has the ability to rock basically in all directions so that it can kind of follow my non-machine-like motion, okay? And you know, what we're doing here is, and that's what these marks are about, and maybe you guys didn't pick up on it, is, yeah, I'm doing this linear stroke, okay, but I'm also moving sideways, okay, a little, you know, about the same amount off this way and about the same amount off this way, okay, as well as that and that, okay, so it's kind of a, you know, I guess a zigzag motion you would call it, right? But it's limiting the, you know, the overhang. And then I do that for a while, and then I clock at 45 degrees, so between the red mark and the yellow mark, and I do the same thing. So I'm rotating this relative to that. And somebody said, oh, you need to rotate that plate. You don't need to rotate that plate, okay? And I've proven it because these plates are pretty flat, right? So the trick is this foam under here, right? So if this was on a solid surface, I might agree with you, okay, that you need to clock this a little bit too. But effectively, we're clocking this relative to that, and then this takes a turn on top of that one too. So we're averaging all this stuff out, and that's how this process works, is it's just magic of averaging, okay? So we're averaging the highs against the highs on this one. While it's on the bottom, then we average it the other way, and then our strokes are averaged out because we're rotating. So there's all this averaging going on, right? And the result of that averaging is that it gets closer and closer and closer to a flat plane, okay? So that's my rebuttal or my answer to the rotation of the lower plate, okay? Okay. All right.